Hello YouTube. So in this video we'll be learning how to find the determinant of a 4x4 matrix. So the most important part of this video is the fact that I'm wearing a sombrero with yellow dye. The reason for that is because I just had an art final, and we'll just leave it at that. Okay, so B equals blah blah blah. We want to find the determinant, so det B. How are we going to do that? We only know how to find the determinants for 2x2s and 3x3s. Those are fairly easy. But what about 4x4? Well, most textbooks would teach you the method of using cofactors, and with that you can find the sum of all the cofactors and multiply by each individual term. But in this video I'll be using row reducing to find triangular matrices. So what's a triangular matrix? So there are two types of triangular matrices. There's the lower half, or the lower triangular matrix, and there's the upper half, or the upper triangular matrix. And what that means basically is that in a lower triangular matrix, all the non-zero terms in the matrix are in this half of the matrix, while the other half has zeros. So for the high, or the upper triangular matrix, all the non-zero terms go in this half, while the other half has just zeros. So for this matrix I have up here, I'm going to be using an upper half, or an upper triangular matrix. So let's first start by using row operations to reduce this matrix to an upper triangular matrix. So I would start by eliminating all the non-zero terms below the 2 in this column 1. So you'd keep this row, and you'd keep these other rows the same as well because they were already zeros. Now you would change this row 1 0 1 1 such that this term over here would become a 0. So how do we so we have to subtract a multiple of the first row. We have to multiply a multiple of the first row to, or we have to add a multiple of the first row onto second row to make this 0. So what multiple would you have to have? Well, it would be -1/2, right? Because -1/2 will lead this to become -1. When -1's added to 1, that just adds 0. So the rest of the terms, this would be -1, -1/2, -3/2, -1. Okay, so now you could add these to this bottom row. So -1 plus 1, 0, -1/2 plus 0, -1/2, -3/2 plus 1, -1/2, this should be -1/2, -1/2 plus 1, +1/2. So this new row becomes -1/2, -1/2, 1/2. And I'll denote this step by saying R2 equals the original R2 minus 1/2 R1. Alright, let's get rid of this. So there's a rule that states that the determinant of the original matrix is pretty much unaffected by the row operation of adding a multiple of another row to a row. So essentially this adding operation, adding 2 rows, does not affect the determinant at all. It stays the same. So if you set, I don't know, the determinant to be, the original determinant to be k, then the determinant of this new matrix would still be k. Okay, now for the next step. Well, we already have everything below this 2 as zeros, so we can start by trying to eliminate these terms over here. So how do we proceed with that? Well, we can keep these the same. These are fine, but we need to get rid of this 2 here. So let's start with that. So to get rid of this 2, what would we have to do? Well, we could try to use row 2, add a bit of row 2 onto row 3, and see what happens. So we have 0, negative 1/2, negative 1/2, 1/2. That would be row 2. Row 3 would be 0, 2, 1, 0. Now we have to multiply this by some factor. We have to multiply row 2 by some factor, some multiple in order to get this term to go to 0. Okay, so this would be negative 1/2 times x plus 2 equals 0. Well, that would be 4. X would be 4. So we have to multiply everything on this row by 4 and add that to row 3. So this would be 0, negative 2, negative 2, 2. So if you add negative 2 to 1, that would be negative 1. 2, positive 2 to 0, that's 2. So row 3 gets reduced down to 0, 0, negative 1, 2. And then you can keep row 4 the same. So what did we do? Well, we added the original row 3 with 4 times row 2. So k would remain the same because additive row operations do not change the determinant. Okay, so we can move on to the next step, which is getting rid of these terms in row 4. Okay, so we could probably try to use row 2 again to eliminate this one term. So let's create a new matrix here. So we have 2, 1, 3, 1. Then we have our 0, negative 1/2, negative 1/2, 1/2, 0, 0, negative 1, 2. Now we're trying to find a new row 3 where this term over here is 0. So we have to add a multiple of row 2 to row 3, or sorry, to row 4 to get rid of the 1. So multiply this by x such that this would be 0, 0, and then something else here. So this would be row 2. This is original row 4, the new row 4. So negative 1/2 times what plus 1 equals 0? Well, 2. So x would be 2. So then what you would add would be 0, negative 1, negative 1, 1. You would add this to the old row 4 to get the new row 4. So our new row 4 would be 0, 0, 1, 4. And this is the result of adding row. So the new row 4 is equal to old row 4 plus 2 our old row 2. Okay, now we're at the final stretch, which is getting rid of this last one to make it an upper triangular matrix. So we still have our 2, 1, 3, 1, 0, negative 1/2, negative 1/2, 1/2, 0, 0, negative 1, 2. Now we want to change row 4 so that this 1, we can get rid of this 1. So this time it's a fairly simple operation. So what we can do is just add row 3 to row 4 because we have a negative 1 to cancel out the original 1 that we had. So 0, 0, negative 1, 2, 0, 0, 1, 4. If you add those up, that's just 0, 0, 0, 6. So we can make our new row 4 entry to be 0, 0, 0, 6, and that would be new row 4 equals R3 plus R4. That's simple. And now we have an upper triangular matrix. And once you have your upper triangular matrix, the only thing you need to do left for the determinant is multiply everything in this diagonal. So we have 2, negative 1/2, negative 1, 6. So our final answer would be 12. Or sorry, 6. Sorry, I forgot how to do math. This art final, it took a toll on my brain. Okay, so this would be the case. The determinant would be 6 because we only used additive operations. Now, let me just cover a bit more theory, and then I'll end the video here. So, if you have, let me just give you like a 3x3 matrix to make it simple. So if you have like, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, you'd say that the determinant, say that this is going to be like A, and then the determinant of A is equal to K. Well, if you were to say switch 2 rows, so like 4, 5, 6, 1, 2, 3, 7, 8, 9. So the result of this switch would be that the new determinant of, I guess this could be A prime, it would be negative K. It would be the exact opposite. And then, so a row switching operation would flip the determinant sign, but keep the determinant the same, the magnitude the same, but flip the sign. And then if you were to do something like 1, 2, 3, 4, 5, 6, 7, 8, 9, if you were to multiply a column or a row, so for example, like if you were to multiply row 1 with like by 4, 8, 12, 4, 5, 6, 7, 8, 9. So say that the determinant of this is K, the determinant of this would be 4K. So it's however many you multiply the original row to get the new row. And then the same would apply if you like multiplied something by the like second or third row. So if you multiplied the third row by like, I don't know, 3, then new determinant would be 3K. So that's more rules for finding the determinant with the row reducing technique. So what that means is that if you have like a determinant, if you want to find the determinant with row reducing, and you have to do like row operations like switching or multiplying without the addition, then you'd have to compensate for the determinant. So for example, if you have like your original determinant would be K, and you had to do like a row switching operation. So you had to do like row 1 equals row 2, row 2 equals row 1. then you find the determinant of this, you get negative K. So in order to compensate for that, you have to make sure to multiply by a factor of -1 because you performed this row operation. And this would lead to the original determinant being K. So oftentimes this can be really convenient and very helpful for efficient computations instead of having to determine every single cofactor to find the determinant of a 4x4 matrix. Anyhow, thank you for watching.